Okay, we are going to begin Chapter 6 with an introduction to vectors. Now, what is a vector? So a vector is a very abstract idea. So it's an abstract idea meaning that I can't actually manifest it into reality. Like it does, if I'm studying a square, for example, that's quite the opposite of an abstract object. Where a square, I can actually cut out a square, physically handle it, measure it, rotate it, flip it, all of that. A vector, on the other hand, is what we call an abstract object, which means I can't actually physically manifest it. Now, what is this object? It basically has, a vector always has a magnitude and direction. And those are the two key components in what makes a vector. So, for example, examples of vector are velocity, for example. Velocity has a speed, right, which is the magnitude, some sort of number value. It's a number value. So the speed is the number value of this velocity. And then it also has a direction. So I can go 10 miles an hour this way. I can go 10 miles an hour north. I can go 15 miles an hour south, whatever the case might be. So velocity has a speed, a magnitude, and a direction. The other one is force. Well, there's a lot more, but another example that's easy to understand is force. So force, for example, I can push this pen really hard, really fast. That has a number value of how hard I'm pushing it. But it also has a direction. I can force it this way, a certain magnitude, or I can push it up a certain magnitude, or wherever. I can push this left, right, up, down, wherever. So the force is something else with a magnitude, an actual number value of how strong I push something, for example, and a direction. Now, what does a vector look like? So what does a vector look like? Well, it looks like nothing. I should say, how is it represented? Right? Because it's an abstraction. It doesn't actually look like anything, but I do represent it. I represent it using what used to be called a ray. Using what looks like a ray. But it's not really a ray. If you remember a ray in geometry, so I'm going to write sort of. If you remember a ray in geometry, started at one point and went forever in one direction. Forever in geo. Right? Starts here, goes on forever. It had no measurements. Because I can't measure forever. It had no measure. Because I can't measure forever. For vectors, however, it has a starting point. I'm going to move over 4 and up 3 for a very... It's almost like a segment with direction. It's more like segment with direction. So it starts here and it does end here. So there is start here and end here. It does have a measure. And that measure, the length of this vector, so vector is not quite a ray, because this actually has a length. So this length right here, this length is the magnitude, represents the magnitude. Now again, the length, for example, the magnitude is an abstract idea. So the harder the force, for example, the longer this length. The faster the speed, the longer this length. Okay? So the magnitude is represented using a length. Okay? And then direction. How do we know direction? Well, direction we usually, for example, if I were to give directions to somebody, there's always some sort of an anchor point, like north. So north would be, I would say, drive north 5 miles, or whatever it might be. In vector form, the anchor is always 0. Always, always 0.
So if I want to say go this way, we use degrees, just like we've been doing up until this point. This theta, degrees, represents the direction. Right? So the direction can go this way, like, what does this look like? 40 degrees maybe this way. Or it can go the other way. It can go 180 degrees, will mean going this way. Yes? And then 270 degrees means going down. A little over 180, 200 degrees might be this way somewhere. Okay? So magnitude is represented by the length of this vector, and the direction is represented by this angle right there. So, vectors, how are vectors written? So how are vectors written? So I'm going to do 4 and 3 again. So because it's not like a ray, I can't actually go past this point. So vectors are written in its component form. So the component form is basically your change of x. It's written with these angle brackets. So these angle brackets, it's written change of x and change of y. Okay? And remember, it does have direction. It has direction. So a -4 would be different than a +4 here. So in this case, if this is the coordinate 4, 3, if this is the coordinate 4, 3, and this is my origin 0, 0, right? The vector form, if I call this vector v, for example, which is a pretty common name, the vector v in its component form is 4, 3. +4, +3. So now what does that mean if I go a different direction? What does it mean by direction? Let's say I went -5, -2. So this is -5, -2. And I'm going to call this vector u, another popular letter to represent vectors. In its component form, so the component form for this vector, u, is going to be -5, because I went in this direction, -5, and the change was down 2. So -5, -2. Yes? So those are what we call the component forms of each of these vectors. Now let's find the magnitude. The magnitude here is the length of this vector, is the length of this vector. And that is your simple Pythagorean theorem. So you have 4 squared plus 3 squared equals to v squared. So 4 squared plus 3 squared equals to v squared. Now v is going to, if you hopefully you don't need the Pythagorean theorem for this particular triangle, because this is a 3, 4, 5 triangle. But in case, here's square root of 25. Please remember, when you square root both sides, you're usually left with the plus or minus 5. But the magnitude is always positive. So we actually take the absolute value of it. So it's actually always +5. So the magnitude is represented using this. It's the absolute value of that vector, v. And the magnitude is +5. It's always positive. So what is the magnitude of this vector here? So the magnitude is written this way. It's also the Pythagorean theorem, which is just the square root of -5 squared plus -2 squared, which is always positive because I'm squaring it. It's going to equal to the square root of 25 plus 4, 29. Okay, so this right here, again, is the magnitude. This right here is the magnitude. Magnitude. It's in there. All right. So the last thing to find right here, right now then, is this angle, the direction. How do we find the direction of this? So this angle right here, you can use your 5 if this is equal to 5. If I know that this equals to 5, I can either use tangent if theta is opposite over adjacent, or sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. So any of those forms will work. I'm going to find the direction using tangent. So I'm kind of out of space. Let's do it over here. So the tangent of theta is going to equal to opposite over adjacent. So then I'm going to take the arctangent of both sides. So I'm going to take my calculator here. I'm going to take the arctangent of 3 over 4. And I'm left with degrees. Make sure that you are in degrees here. 36.87 degrees. 36.87 degrees. And this right here is the direction. Okay? So I found my magnitude is the length of the vector, and the direction is this angle. So right here then, we found the magnitude of this vector u. Let's find the theta. So the angle, the direction. Now this angle here is going to be, so I'm going to use tangent again. Tangent of theta is opposite over adjacent. Now if you notice, if I take the arctangent of 2 over 5, which is the same thing as negative 2 over negative 5, I get 21.80. So theta is approximately 21.80 degrees. Now that is not the direction of this vector. Why isn't it the direction of this vector? 21.80 degrees is actually this way. It's an angle that looks like this. 5, 2. So like this is 21. This vector going this way is 21.80 degrees. The angle that we want, the actual direction of my vector, is this right here. So let's name this alpha. So this is my direction. The actual direction is going to be 180 plus that 21.8. So this is going to be plus 180. I get 201.8. 80 degrees. This right here is the direction of my vector u. So it's over 180 degrees. Okay? All right. Next.